Hi, I'm Sam Sly.
I'm Quinn Jarecki.
And I'm Bobby Urswich, and this is Optics 380A, Lab 11 on diffraction. For the first part of this lab, we were looking at the qualitative behavior of diffraction patterns resulting from a 550 nanometer laser impinging on single slits of varying size. We started with a single 160 micron slit. As we push the camera back along the optical axis, we move through the Fresnel region. In the Fresnel region, we can see the single peaks which indicate various Fresnel zones. We calculated that the Fraunhofer, or far field region, begins 118 millimeters behind the object module. As we used single slits of increasing width, we observed that the fringe spacing increased and the length of the pattern decreased. When we switched to double slits, we observed the interference as well as the diffraction pattern. As we increased the spacing but not the slit width, we observed that the peaks in the diffraction pattern became smaller and increased in number. As we increase slit width but not spacing, we observed that the diffraction pattern shrinks and the peak gets wider. Next, we used the circular aperture. In the Fresnel region, we observed the radially symmetric Fresnel zones, which increased the number as the camera was brought towards the aperture. In the far field, we observed the airy pattern. For the square aperture, we observed the Fresnel zones as two perpendicular, linear Fresnel zone patterns. In the far field, we observed the sync function. For the triangle aperture, we observed the Fresnel zones as three linear Fresnel zone patterns, each perpendicular to one side of the equilateral triangle in the far field. We observed that the diffraction pattern expanded out from the sides of the triangle as curved lines.
For the second part of this lab, we used a 200 by 400 micron aperture. We captured an image of the Fraunhofer diffraction pattern from the ThorCam program and imported it to MATLAB, where we fit the sync functions to the two axes of the diffraction pattern. From this, we calculated I by I naught for the first maxima to be 0.0469. This results in a 4.3% error from the expected value of 0.045. We calculated I by I naught for the second maxima to be 0.0163, which gives a 1.7% error from the expected value of 0.016.
For the second part of the lab, we used a 500 micron circular aperture. Again, we captured an image of the Fraunhofer and imported it to MATLAB. This time we fit a sombrero squared function to the diffraction pattern. For this, we calculated the I over I naught for the first maxima to be 0.0173. That results in a 1.3% error from the expected value of 0.0175. We calculated the I over I naught for the second maxima to be 0.00399, which gives us a 0.12% error from the expected value of 0.0042.